Is it conceptually possible to build a functioning highway literally hovering 3,000 meters above the abyss? Geologists initially called this project technical suicide. 3,000 meters is the cruising altitude of a light aircraft. Below the asphalt lies only fog and a vertical drop. Standard road construction demands stable ground. Here, the ground does not exist. The environment in Sichuan dictates extreme physics. Hurricane winds batter the exposed cliffs constantly. The tectonic reality is brutal. This fault line generates earthquakes reaching magnitude 8. A shock wave of that scale violently snaps standard concrete pillars. Gravity pulls down. Seismic waves tear horizontally. Conventional engineering fails immediately. Yet the highway stands. It clings to sheer rock without massive support towers underneath. Taming these extreme forces required an absolute defiance of traditional mechanics. The highway survives by gripping the mountain face from the inside, relying entirely on a massive grid of invisible anchors. While invisible anchors secure the highway in the sky, the southern Yunnan-Guizhou Plateau presents a completely different gravitational nightmare. Engineers faced a brutal physical problem, safely lowering a heavy freight convoy down a 2,000-meter cliff. The regional karst topography is essentially a shattered landscape ending in a massive geological step, 2,000 vertical meters, a solid stone wall. A conventional alpine road requires endless zigzagging switchbacks. That means ruined transmissions, runaway trucks, and the acrid smell of burning brake pads. Designers bypassed the exterior entirely. They folded the highway inside the mountain. Massive machines carved a giant corkscrew directly through the solid rock massif. A column of heavy trucks drives into the heart of the stone, gliding steadily down an illuminated, continuously curving tube. The spiral tunnel acts as a structural decompression valve for extreme altitude. It wraps the immense vertical drop into a mathematically controlled descent. This geometry translates a deadly 2,000-meter plunge into a gentle 3 to 4% gradient. Constant speed, zero gravitational panic. After completing the subterranean loops, the transport column simply rolls forward. The vehicles emerge into daylight hundreds of meters below their original entry portal, yet they are still driving deep within the belly of the mountain system. While engineers in the southern plateaus tricked gravity with elegant subterranean spirals, the northern border demanded a radically different approach. Here, finesse was useless. Crews had to ram straight through a 100-kilometer wall of solid granite. Brute technological force. The Qinling Mountains stand as a massive geological barricade dividing the climate zones of the continent. To breach this vertical fortress, engineers deployed intelligent tunnel boring machines. The giant steel rotor spins. Tungsten carbide discs smash into super hard rock. A dull, monotonous vibration pulses through the shaft as tectonic sensors scan the surrounding massif in real time. Laser guidance systems align the cutting head with absolute precision. Zero deviation. The ancient stone yields. The mountain range is exactly 100 kilometers wide, a span equivalent to crossing a small European country. Construction teams converted this impenetrable barrier into a straight, hollow transit pipe. 90% of the entire route now runs deep underground or glides over towering viaducts. No steep gradients, no sharp turns. This flawless linear trajectory allows transport streams to maintain a steady velocity of 250 kilometers per hour. For centuries, traversing these peaks required a full 24 hours of deadly driving along narrow, snow-choked passes. A single slip meant a fatal drop into the abyss. Today, that perilous climb is permanently erased. Transports simply dive into a brightly illuminated, secure corridor cut directly through the tectonic fault. The entire crossing now takes less than 1 hour. The localized technological victories over deep karst voids and dense granite led to a single overarching achievement. Engineers hacked the geographical macro system, shattering the 1,000-year natural prison of the Sichuan Basin. Geologically, this region forms a colossal stone bowl spanning over 200,000 square kilometers. For centuries, steep mountain ranges kept the territory completely cut off from the outside world. The 8th century poet Li Bai historically marked this absolute isolation, defining the local borders as harder to cross than the sky itself. He documented a strict physical reality. Leaving this terrestrial island meant navigating primitive trails bolted directly into vertical rock. Rotting wooden planks emitted a dry creak underfoot directly above a bottomless abyss. Today, high-strength steel viaducts systematically replace those sheer cliffs. Wood yields to metal. This precise material substitution triggered a massive geopolitical integration of the entire southwestern territory. The continuous This network of modern infrastructure forcefully pulled tens of millions of residents out of geographic exile and locked them into the global economy. Geography no longer dictates fate. The geological bowl is cracked wide open. However, successfully overcoming the Qinling mountain range through spiral tunnels serves merely as a preliminary warm-up before the ultimate test. Conquering the deep western permafrost and bridging the violent rivers below demands a radical shift toward fundamentally different engineering solutions. The transition from underground tunnel boring to the construction of high-altitude suspension megastructures over the Dadu Gorge begins with a paradox. The canyon forms a deep geological wound. Hurricane-force winds funnel through the narrow gap. A constant aerodynamic hum vibrates through the metal. Building support pillars in the riverbed guarantees structural failure. The Xingkong Bridge bypasses the ground entirely. The deck hovers more than 200 meters above the rushing water. That matches the extreme height of a 60-story skyscraper. The main span stretches over 100 meters across the abyss. Yet the defining feature of this engineering marvel remains completely invisible. Standard suspension cables require massive concrete gravity anchors. The near vertical canyon slopes provide zero flat terrain for such monoliths. The paradox forces a radical structural shift. When you cannot build an anchor on the mountain itself becomes the anchor. Engineers drill directly into the cliff face. Two enormous descending tunnels pierce the solid granite. Thick bundles of steel cables slide into the absolute darkness. High-pressure concrete seals the cavities. Metal and stone fuse together. The sheer mass of the mountain now counteracts the immense tension of the suspended deck. The external contrast is absolute. A seemingly weightless red structure visually floats across the sky. Hidden beneath the surface, the structural grip locks deep into the earth, driving the main steel cables into the solid rock for exactly 159 meters. But this is only a local solution but the 159-meter anchors of Dadu are merely a response to the baseline geology of the Hengduan Mountains, where the earth is capable of tearing standard concrete to pieces. The average altitude here exceeds 4,000 meters. This is a vertical maze of perpetually frozen ground. During the brief warm hours, liquid moisture seeps deep into the pores of conventional building materials. At night, temperatures plummet. The trapped water turns to solid ice, expanding with a microscopic crunch that shatters the internal matrix from the inside out. This relentless daily cycle of freezing and thawing stands as the absolute primary enemy of structural engineering. Standard mixtures simply turn to dust. Builders counter this threat by deploying next-generation polymers and highly specialized concrete. But surviving the ice demands massive resources. Every kilometer carved through this hostile territory costs 10 times more than an equivalent stretch on the flat plains. That massive financial premium buys vital resilience against an even deeper threat. A magnitude 8 earthquake releases enough kinetic energy to snap standard rigid pillars like brittle chalk. Deep below the permafrost, active fault lines constantly grind and fracture the valley floors, forcing the solid rock to violently shift, which demands the creation of flexible megastructures. This tenfold increase in seismic adaptation costs culminated in a €3,100,000,000 project, the 240-kilometer Yaxi Expressway, a continuous megastructure driving into the sky. This massive highway spans a distance equivalent to the gap between two major European capitals, hanging entirely in the empty air. The road functions as a giant uninterrupted ramp. Every single kilometer, the asphalt steadily climbs 7.5 meters, a relentless physical ascent. Wind howls through the deep gorge. Ice-cold mist coats the structural steel. Visual perspective glides vertically along the Labajin Viaduct. Colossal hybrid pillars rise 229 meters from the fractured valley floor. Further up the route, at an altitude of 2,500 meters, the Ganhaizi Bridge confronts highly unstable mountain slopes. Standard monolithic concrete pillars would immediately crush the fragile soil beneath. To solve this, engineers deployed a radical weight reduction technology. The primary load-bearing skeleton consists of immense hollow steel tubes. Powerful industrial pumps force high-strength liquid concrete directly into these empty metal shells. The physics operate flawlessly. The outer steel restricts the concrete, preventing outward expansion and brittle cracking under pressure. Simultaneously, the dense concrete core stops the thin steel walls from buckling under extreme vertical compression. Maximum load capacity, minimal dead weight. When tectonic waves strike the gorge, these reinforced hybrid pillars subtly sway, absorbing the destructive energy without snapping. Building this continuous alpine ramp requires the precise manipulation of thousands of heavy composite components suspended over the abyss. Executing such a complex assembly by hand represents a volume volume of work that would take decades using traditional methods. How do you deliver and secure hundreds of tons of concrete where building scaffolding is physically impossible? Assembling 240 kilometers in the void without scaffolding was made possible by full mechanization and the 580-ton monster SLJ-900. It is a mobile robot factory, 92 meters long, 580 tons of heavy steel. That is the equivalent weight of a fully loaded passenger airliner balancing on the very edge of a narrow concrete pillar, suspended directly over an abyss. The operation follows a strict mechanical algorithm. First, the unit transports a massive prefabricated concrete segment from the casting yard to the absolute edge of the finished road. The sequence begins. The forward frame pushes out horizontally over the open drop. It extends forward, entirely unsupported, until the front legs reach the next isolated pillar. Hydraulic supports deploy with a heavy metallic clank. The frame locks tight. The vehicle temporarily transforms into a rigid steel bridge. Next, the massive concrete section glides forward along the machine's underbelly. Heavy winches lower the block. Millimeter precision, zero margin for error. While mapping drones and tunnel welding robots handle the peripheral terrain analysis, this specific mega machine single-handedly dictates the construction pace. Bypassing hazardous valley scaffolding accelerates the timeline completely. Mega projects that historically demanded decades of manual labor now reach completion in exactly 5 years. The heavy block lands, the steel arms retract. The automated operation of the 32-wheel bridge layer SLJ-900 proves that it is possible to lay a route directly through the air, leaving the mountains untouched, which brings us to the systemic level of ecology and economy. Ecological standards, for which mega machines like the SLJ-900 were created, became just a warm-up before the most complex project in history, punching through the Yarlung Sangpo Canyon. The Sichuan-Tibet Railway requires a staggering investment of 40 billion euros. That equals the financial reserves of an entire European nation poured into a single transport corridor. To cross the deepest gorge on the planet, engineers must carve tunnels extending over 30 kilometers straight into a highly active tectonic fault line. 40 billion euros, 30 kilometers, 40 degrees Celsius. A massive tunnel boring machine slowly grinds into the mountain face. Giant steel cutter heads chew through ancient quartz and granite. From the sheer walls of the canyon, thick steam rises into the freezing high-altitude air as geothermal heat escapes the freshly cut shaft. Inside the tunnel, there is no ventilation system capable of fully neutralizing the Earth's core radiation. The crew operates in a suffocating, heavy atmosphere where the bare rock itself bakes the air to 40 degrees Celsius. Engineers plan to launch the first trains by the year 2030. Here, modern heavy machinery pushes its absolute physical limit against the raw mass of the Tibetan Plateau. The main threat is not just the extreme underground heat or the total geographic isolation. Deep inside the mountain, tectonic forces compress the cavern with a weight equivalent to a vertical ocean of stone. At this depth, the accumulated geological pressure exceeds tens of megapascals, causing solid granite to violently explode right out of the tunnel walls. But while punching through rock at 40 degrees Celsius and raising concrete megastructures, engineers are solving a pragmatic problem, not disrupting the physics of the external landscape. Carving a traditional road into the unstable slopes of Sichuan triggers an immediate geological chain reaction. Slicing away the mountain base removes the natural anchoring mass holding the terrain together. Gravity takes over. Thousands of tons of fractured rock slide downward. Total destruction. The financial drain of deploying fleets of excavators to clear seasonal landslides over a single decade vastly exceeds the initial price tag of suspending a high-tech viaduct across the valley. Eco-friendly design is not charity. It is pure economic survival. Bridges bypass the danger zone. Massive pillars elevate the highway high above the forest floor, allowing local wildlife to slip unnoticed beneath the concrete canopy. But the ultimate engineering contrast emerges between the brutal force of excavation and the surgical precision of fluid dynamics. Industrial rotary drills shatter solid granite, generating massive volumes of toxic, sediment-heavy slurry. If this abrasive sludge breaches containment lines, it instantly suffocates pristine mountain mountain rivers. To prevent an ecological collapse, crews deploy closed-loop water recycling networks directly on the cliff edge. Dirty construction runoff channels into primary settling tanks where chemical coagulants aggressively bind the microscopic rock dust. Heavy sludge drops to the bottom. The remaining fluid forces its way through dense mechanical membranes, stripping out the finest abrasive particles. Purified liquid cycles straight back into the machinery to cool the glowing drill heads. Industrial centrifuges spin without hesitation, continuously extracting dry rock cakes from the endless, roaring flow of wastewater. Ecological overpasses and water recycling systems are merely the physical framework. The true target of the project lies squarely on the macroeconomic plane. For decades, moving freight from high-altitude agricultural zones to consumer hubs was an agonizing logistical chokehold. This was the reality of the old route. A driver grips the steering wheel with white knuckles, fighting the exhausting tension of a blind mountain serpentine. The diesel engine screams. Heavy rain turns the narrow dirt pass into a trap. In the back of a stalled truck, crates of high-value agricultural goods slowly rot under damp tarps. Mountain transit delays routinely wiped out 30% of the cargo value before it ever reached the city limits. That was the 48-hour agony, a grueling, dangerous crawl. Then the timeline fractures. Today, a continuous roaring flow of 40-ton semi-trailers gliding over smooth asphalt replaces the stranded trucks. The supply chain math rewrites itself. A transport operation that devoured 2 full days of fuel and risk now takes under 4 hours. Total system reset. The financial friction vanishes. Hauling heavy construction materials and temperature-sensitive medical supplies into the highlands costs drastically less. This sudden velocity physically erases geographical isolation. Autonomous prefectures, once locked out of the market by extreme topography, instantly plug into the national economy. Casual tourism expands, but the core revolution remains strictly industrial. Infrastructure acts as a macroeconomic defibrillator. The new transit corridors do not just bridge physical gaps across the valleys, they accelerate regional logistics speed by 1,200%. To comprehend this leap from 48 hours of isolation to global integration, it is necessary to look inside the structures themselves. Concrete and steel conceal a continuous microscopic war. Artificial intelligence simulations strip away the outer shells, generating precise digital twins of the entire transit network. Algorithms process billions of structural variables. They visualize the invisible. Thermal stress points glow crimson at the suspension joints. Acoustic microvibrations ripple through the digital concrete model. This algorithmic scan exposes the raw mechanical limits that human vision cannot capture, turning massive engineering into an intricate anatomical display. Every pillar and tunnel stands as a calculated victory over absolute geological hostility. Which of these engineering monoliths demanded the most radical defiance of physics to conquer? The data models map the hidden forces. Engineering breaks the mountains. The next frontier of knowledge